Looking here at the normal distribution, this is described in the text in some detail here in chapter 4. This is on page 25 of the text. The normal distribution is shown as this bell-shaped curve that many of us will be familiar with. Invariably, the y-axis is not shown, but the y-axis is always assumed to be a frequency scale. That is to say, and the x-axis here is the range in values that we observe for the population. At the low end we have very low values that we observe, and at the high end are the large values that we observe. In the middle here are the mean or average values defined by mu, the population mean. So if we were to go and measure, for example, leaves on a tree, we're going to find some small leaves. We're going to find a small number of large leaves, and we're going to find a large number, that is a high frequency, a large number of average size leaves. And so by sampling a large number of leaves and drawing the frequency distribution, for most of our biological data is going to fall onto a normal distribution. The variability is shown by the population standard deviation, and for a low standard deviation will be a taller, more narrow curve. So if we had a smaller standard deviation with the same mean, would rise a higher frequency and a lower frequency of the extremes. A high standard deviation will be a flatter, wider curve. Features of this we'll talk about more about these features, but typically at 2 standard deviations, approximate or mu plus 1.96 standard deviations will be exactly 95% of the population, and often this 95% range is a comfortable range that we can be happy that most of our data, that is 95% of our observations, fall within mu plus or minus the two standard deviations. 2.5% are going to be larger than the mean plus 2 standard deviations, and 2.5% in this range smaller than the 2 standard deviations. Another important measure we use in statistics is the standard error of the mean, and that is the accuracy of a sample mean, or that is to say how well that sample mean predicts the population mean. When we take a number of samples from a population, we're using that sample as an attempt to represent the population, and we can use the standard error as a measure of how close the sample mean is to the true population mean. We will use measurements of samples to compare means of samples from different populations and make estimations as to whether those means from those different populations, that is with one treatment compared to another treatment. The standard error is calculated as the standard deviation divided by the square root of the number of samples that went into that population, into that sample from that population. It is calculated, can also be calculated as the variance divided by the number, and that term all square rooted. These two calculations give the same calculation. So the standard error is a measure of the accuracy. There are two components that contribute to how accurate is a mean of a sample from a population. The two components are both the standard deviation of the sample that we use, and inherently variable data will be less accurate and will be more difficult to find differences when we compare means if we have high variation, but also the number of samples, and we can improve our estimate of a mean by taking more samples. For us as researchers, more samples invariably requires more time, and so it's a trade-off between how variable our population is and how much time we have to be able to sample, keep making those samples. Testing for normality. We'll spend more time later in this course testing for normality, but it is very critical for us to know whether our data indeed represents a normal distribution or not. One of the implicit assumptions in all our statistical theory is that we are using a normal distribution, and deviations from normality will undermine our ability to be able to make valid tests. In Excel, it is not easy to test a population as being normal. We can try this in the next recitation. Excel is able to create a normal distribution, an arbitrary normal distribution, and we can compare our observed distribution with a theoretically normal distribution and use a chi-squared test to determine whether our observed distribution fits a normal distribution generated within Excel. But in SAS and R, we have some very nice tests. In SAS, we can use PROC univariate normal. It's a very easy procedure. It quantitatively tells us if our sample from a population is normal. It also gives some other parameters, including kurtosis and skewness. In R is typically a lot more conservative in terms of the type of output, and we can use the Shapiro test, will give us a quantitative test of normality. So that concludes some introductory concepts. Next week we'll be looking a little bit more about the normal distribution in a bit more detail, and how we use the normal distribution to make hypothesis tests. So until that time, you should now proceed to the recitation exercise and work through some of those calculations using some experimental data.